Okay, we've got Alex Plaskett from MWR next, who's got what I believe is the first working Windows Phone 7 exploit.
Yeah.
Okay, awesome. Right, so Noel there at the front end. So you can give Alex a warm welcome, that'd be great, thanks.
So, hello, welcome to my talk on Windows Phone 7. I just want to go over the main objectives of the talk to start off with. I'm going to hopefully provide an overview of Windows Phone 7 for those of you in the audience who aren't familiar with Windows Phone 7. And then I'm going to talk about the security features and the security model and all the protections which Microsoft have implemented to protect the phone. And then after that, I hope to highlight any potential weaknesses which I've discovered throughout this research, and also demonstrate exploits which I've written to exploit these weaknesses. The target audience of this presentation is really for application developers, security professionals, and pen testers. So they understand the platform security better, because currently there's very little information on the actual security which Microsoft have implemented. So myself, I'm a security consultant at MWR, but ultimately I've been breaking stuff for quite a long period of time, and mainly in offensive security. So the talk, I'll start off with the introduction for those of you who don't know about Windows Phone 7 and don't know about the ecosystem. Then after that, I'm going to speak about the security model, the features, and then finally the vulnerabilities. Okay, so because this is a brand new research area, there's been no previous presentations on Windows Phone 7, then I hope to have quite a wide coverage of the security, but I'm not going to go very deep in a certain number of areas. So I won't be touching on managed application security, cloud storage, or UAX native applications. I hope to cover those in further research. So Windows Phone 7 phones themselves, there's currently a lot of manufacturers out there which make the phones. It's not just one phone, which is like the iPhone, for example. And so there's a number of OEMs, the original equipment manufacturers. And each of these OEMs might have a number of phones as well. But ultimately, it's the same base operating system across the range of phones. But there's customizations for the OEMs, such as device drivers to support that platform, and OEM applications which provide extra functionality over what a normal developer would get. It's a closed platform. There's no way really that the end user sees the operating system. You can't make very many changes. Well, you can't make any changes to the operating system other than the settings which you normally see on smartphones. The operating system itself, it's based on Windows CE. It's somewhere between CE 6 and CE 7, I think. But it's heavily customized for Windows Phone. It's the processors which are in use, they're ARM architecture at the moment. All the phones are ARM. It's 32-bit OS, so that gives you a 4 GB virtual address space, which is divided up into 2 GB for the user land and 2 GB for the kernel. And then finally, the updates for the operating system, they're pushed out via Windows Update and Zune tethering. And updates are signed, so you can't just apply malicious updates to the phone. They have to be correctly code signed by Microsoft. Now, I think to really understand the security model, you have to consider the application development lifecycle. third-party applications, third-party developers, sorry, which are not the OEMs or the mobile operators, they're only allowed to write managed code, such as C# on using Silverlight and the XNA framework. But OEMs are allowed to write native code, so they have greater level of access to the actual device. There's also no way of side-loading applications to the device unless you've got a developer-unlocked device or you've used a hack such as Chevron to essentially develop and unlock your device. Then all applications have to be submitted to the marketplace. They go through a verification process, and then Microsoft code signs the applications to allow them to be loaded to the phones. So the Windows Phone 7 security model is, there's a number of key subsystems which all work together to maintain the security of the phone and protect the data which is stored on the phone. The first one of these is the concept of chambers, the chamber-based security model. So chambers are essentially virtual execution environments for processes on the phone, and they restrict what access the processes have to data, depending on what chamber the application is running in. So it's like a sandbox where it restricts what the application can access. And these are divided up into a number of privilege levels. The trusted computing base at the top, that's where the kernel and the kernel mode drivers are running. And it's also where the security of the phone is enforced from. So if you want, you can consider the trusted computing base as maybe system on a normal Windows operating system, the highest permission, the highest privilege account, and it gives you full access to everything on the device. So if you compromise the TCB, then you can get everything. Then you have the elevated rights chamber. Elevated rights is for applications which, well, for services which need to be published globally across the device. Then you have elevated rights is things like user mode device drivers, ones which don't need to run in the TCB, and yeah, and then you have the standard rights chamber. Standard rights chamber is where the mobile office runs. It's for native code applications which don't require high permissions, but still need to run, still need access to non-globally accessible services. And then finally, you have the least privilege chamber. The least privilege chamber is it's where the marketplace applications, when you install an application from the marketplace, that's downloaded and deployed with the permissions of the least privilege chamber. Now, the first three chambers, the TCB, elevated rights, and standard rights, they're fixed permission sets, so you can't change the permissions of those. They're all defined by the security policy in the operating system, which I'm going to cover later on. But the fourth one is special because the fourth one, the least privilege chamber, is controlled by capabilities in your application. So that when you're developing an application, then you specify what capabilities the application requires. So these are, by default, the least privilege chamber is really restricted. Your access to the file system is really locked down, and you need to, if you need access to security or privacy critical functionality on the phone, then you need to specify a capability for the functionality which you're looking for. So for example, if you need access to the location services or the camera, then you need to specify that capability in the manifest file. That's the WP manifest talks about when you're building your application. The next bit of Windows Phone security is the code signing mechanism. Everything which is built into the ROM when the operating system is built is implicitly trusted by the device. It doesn't need to be code signed with a digital certificate. but everything else which is added to the phone afterwards, that requires you to code sign with a trusted code signing certificate. There is one exception to this, which is developer unlocked devices. They need that for testing purposes. Then you can test unsigned code on the device. So that's the exception. So how this works is there's a code signing certificate store, this ci-roots.pks on the device. And for each, so these certificates map to the chambers. So you have a trusted TCB certificate for the trusted computing base. So anything which is signed with a certificate which changed to, with the certificate authority of this one, then essentially can load to the trusted computing base, as long as there's a policy entry on the device as well. There also needs to be a file, there also needs to be a definition in a policy file to allow this to occur. So here's an example of a policy file. So this basically says that the SHA-1, a certificate which has got the SHA-1 hash fingerprint of that value, if the code is signed using a valid certificate, then that can load to the, that's the SHA-1 hash value of the TCB certificate. And there's a user account, that's the SID, the user account of the TCB chamber. So this policy specifies that you've got execute access to the TCB chamber as long as your code's signed with that certificate. All this is enforced in the kernel. And it's a kernel-based module. It controls all the authentication and authorization on the phone. This is also running in the TCB. So to bypass any of this, you really need to compromise the TCB. This works by, so the load verifier is kind of the gateway, the gatekeeper to security on the phone. It essentially enforces the policy, enforces the code signing, and does all the security critical functions on the phone. There's two files which are important in this, two database files. There's accountdb.vol, which is the account database, which has got users, groups, roles, and so on. And the policy database, which is the security policy of the device. And there's three functions which are used in the load verifier module. Now this is partially documented in Windows CE 7 documentation, but because Windows Phone 7 has been heavily modified, then the functions which are in CE 7 aren't like the ones in Windows Phone. The loader verifier authenticate file is used to authenticate whether the code is signed with a valid digital certificate for the device. And then this returns an authentication information for that file, which you can use with the load verifier authorize to determine whether the code has permission, is authorized to perform an action such as loading from one chamber, the currently executing chamber, into another chamber. And then finally, you have the loader verifier provision security for application. So when a new application is installed, from the marketplace, for example, the capabilities and so on are parsed, and the security for that application is the policies are created, the user accounts and the groups are created for that application which you've just added to the phone. So the policy framework, which I've been talking quite a lot about policy, well, how this works is that when Microsoft have designed the operating system, for each of the modules in the OS, they specify an XML policy which dictates what functionality that module exposes, and everything else is restricted. So unless you have a policy entry which says that this functionality is exposed, then if an attempt's made to access that functionality, then it'll just be denied by default. And then all these XML documents, they're basically, they're all compiled into one big policy document. and then that's built into the policy database, a proprietary policy database which is used for fast lookups of policy entries when a policy decision needs to be made. This is also protected by the trusted computing base as well. So if you want to compromise the centralized policy, then you have to compromise the trusted computing base to get at this. So how this works is there's a number of resource identifiers which are used to, it's the hierarchical namespace. And everything, so you can specify these resource identifiers for things like the registry, the file system, the resources. And so this top one, for example, is like HKey, current users, software, Microsoft. And you can use wildcard matching as well. So everything underneath that key is the policy is applied to when a policy check occurs. And here's an example of the policy as well. So the policy specifies whether, so this one here specifies that Windows/taskhost exe, which is where all the managed code applications are actually hosted on the phone, specifies that it has execute and load permissions to load inside of the task host chamber. And for every binary, for every program on the phone, then there needs to be a policy entry allowing that binary to load. So you can't just put a file on the phone and expect it to work, because they won't. Also, in normal Windows, to create a process, you call the create process function from Win32 API. It's similar on Windows Phone 7, but the process creation is also protected by the policy as well. Here's an example from Internet Explorer. So Internet Explorer is allowed to, see account can launch, so Internet Explorer is allowed to launch the cprog, which is the phone dialer. But if that policy entry isn't there, then Internet Explorer is protected from launching any other binaries other than the ones which are specified in the policy as well. And resource requests as well. When you access a resource, such as the registry, the file system, and so on, a policy check is performed to determine whether the policy can be, whether the policy allows this to occur. And finally, exploit mitigation. Now, there's a number of features which are implemented to make it harder for an attacker to write exploits against the platform. You've got address space layer randomization, ASLR, which, for those of you who aren't familiar with that, it basically randomizes the virtual address space of that process so that the attacker can't determine where in memory certain bits of data are. So if you're looking for a buffer in data, which you put your shellcode in, for example, then you don't know where it'll be, so you can't just directly jump straight to that buffer or that kind of. There's also execute never as well, which is execute never's ARM architecture is equivalent to non-executable memory protection. It basically enforces that data which is written can't be, doesn't become executable. So if you've overflowed a buffer and you try executing the code, your shellcode which you've injected, then because the code will be marked as non-executable and the hardware will prevent that code which you've injected from becoming executed. That's it from the security features and the security model of the phone. I'm now going to talk about the exploit development process I used to develop exploits against the platform. So the first thing I wanted was some way to get debugging on the phone. It turns out that tittled, which is the normal way of debugging Windows CE, is totally stripped out of production ROMs, so you can't do any normal debugging. But it is possible actually to enable error reporting. If you've ever seen Dr. Watson pop up where the process has crashed, then it's the same as that. It's post-mortem crashes when the program crashes. A fellow security researcher, Kevin Finister, found a way to do this and blogged about it on his blog. But the problem now is that you can't. So you've got crash dumps on the device. A process has crashed, but you can't get the crash dumps off the device because the sandbox in the least privilege chamber protects the file system. So you can't access the crash dumps. So you need to find a way of getting the crash dumps off the device. So there's this capability which you can give to dynamic to C# applications, normal third-party developer applications, which is entirely undocumented, and it's called ID cap interrupt services. Now, this capability seems to be used by the OEMs and mobile operators to have extra permissions and extra functionality of the device. And it can be used to bypass the security policies which are applied to the least privilege chamber by using this OEM functionality to read and write files. So you can use this functionality to gain access to the crash dumps. And when you've got access to the crash dumps, you can copy them. You can send them over HTTP off the device, and then start debugging normally in WinDBG. Open the crash dump up and look at the registers and stack and so on. The next thing I wanted to do was to have access to the code as well, the files and the programs which were used on the device. This requires you to rebuild the modules because on Windows CE, modules aren't normal PE files. They're actually, all the PE headers are stripped and they're in sort of sections which, so they can execute on the file system. As ROM file system. So that requires rebuilding the modules to PE files, and then once you've done that, you can start reverse engineering them in IDA. So at this point, you've now got a working environment which you can do debugging, but you're severely restricted as well because the error reporting is limited to context dumps. You have 128 kilobytes of data in your context dump. So you have the registers, you have the stack frames, and you have a few bytes around the instruction pointer, but you don't have very much else. It makes it quite difficult to write an exploit with only that information. But yeah, carrying on. So I audited the binaries and looked for vulnerabilities, and I found a way of getting initial code execution on the device. But you've got I found a way of getting control of the program counter, which is essentially you've still got to beat the exploit mitigation techniques which are implemented in ASLR and XN to get full arbitrary code execution. So me and my colleague Nils sat down and we thought about this for a while, and we figured out a way of bypassing the ASLR and XN, and we got around that protection. And then achieved code execution in the least privileged chamber. But I didn't really just want code execution in the least privileged chamber. I wanted to find a way to, because the problem is with just code execution in the least privileged chamber is that you're limited to the application which you've exploited, the files which the policies allow you to access for that application. So say you exploit the web browser, you're limited to the cookies, the history, all the files which the web browser uses, but you can't access the SMS database or the contacts or anything like that. So you need to find a way of elevating your privileges up to a higher privileged chamber, such as the trusted computing base or elevated rights chamber. So you need to find a priv-esque vulnerability as well. Okay, so I'm now going to talk about the vulnerabilities which I found throughout this research and demo and exploit which I wrote against the platform. I had a feeling that the OEMs were not going to be up to the same kind of code quality and security as Microsoft's code. So I started auditing all the OEM applications and to determine what functionality the OEM applications were using and what additional functionality they'd written for Windows Phone 7. So the first thing I did was, well, I thought it'd be nice to be able to figure out how to deliver a payload specifically for the phone which you were targeting. So if you're targeting a Samsung phone or a HTC phone, it'd be nice to be able to determine remotely what phone you were targeting and then vary your payload depending on that. Okay. So to do that, so the browser agent actually exposes what type of phone it is, whether it's HTC or Samsung or anything. Actually, I've spoken about this already. This is the code execution vulnerability, which gave me control of the program counter. But at this point, you still need to beat the exploit mitigation as well, the ASLR and the XN. So, but I can't, that method is, the way we bypassed it is currently unpatched by Microsoft, so I can't go into how I bypassed that, unfortunately. But as soon as it's patched by Microsoft, then I'll release full details of that. So at this point, I was looking at ways of doing privilege escalation. As I spoke, the interop services capability, it's undocumented, but you can access it using reflection. So you can instantiate the binaries on the phone. You can do that by also by adding this WP interop manifest, and then that gives you access to the COM interop capability. So I started, I audited the device drivers as well for a HTC phone. And it turns out HTC had written a device driver which gives you arbitrary read and arbitrary write access to the entire memory space of a process. That's included the kernel memory space as well. So clearly, if you can write to the kernel memory space, then you can gain code execution in the context of the kernel as well, and bypass all the security which is implemented in the TCB. Don't really know why they had that in there, but. So the way I did this was, there's a K data struct which is at a fixed memory location mapped to every process. And if you walk through the data structure and go through, dump the data out of it, you can locate pointers to system calls. This is quite an old school technique of patching system call handlers to point at attacker controlled code. And then when another thread comes along which is executing in a higher privilege context, then the code will be executed with that higher privilege context. So I dumped out the data in there, located a bunch of C-info structs which had pointers to API sets. API sets are Windows C's method of implementing system call dispatches. So my aim was to patch a system call dispatcher, and then once the system call was called, then in a high privilege context, then it would be redirected to my own shellcode, and then that would execute in the context of a high privilege process. So this is just a case of going through all the data structures and then patching the pointers, the function pointers, to point at your shellcode. And then that way you've got, that's TCB code execution. So I was wondering whether these vulnerabilities were just HTC or whether it was other OEM manufacturers out there which had introduced these kind of vulnerabilities. So I started looking at device provisioning. Device provisioning is it's for configuring phones with a device provisioning server, and you can push out provisioning XML documents to reconfigure certain features. But it also gives you access to the file system, to the registry as well. So I was thinking maybe I could use the file system access to get sensitive files like the SMS database or the contacts and things, because so I looked at the binaries which we used for device provisioning on Samsung as well, and I found a directory traversal vulnerability on one of the binaries on Samsung. It's just a simple WSPrintf window sanity checking on the path which you provide to this. So this RAPI config, which handles the device provisioning, it can only read files outside in the prov XML directory, but as a least privilege application, you don't have access to this directory. So I needed to get it to read somewhere which I did actually have write access to. But managed code, it has isolated storage folders. And these isolated storage folders map to a native path on the disk. So you can write your device provisioning XML document in there. But there's also another problem, is that you don't have permission to spawn new processes either in the least privilege chamber. Turns out that Samsung had been nice enough to implement a method of spawning new processes in a device driver. So it's just a case of finding the right device I/O control code and the buffers, the data you need to pass to this, and then that bypasses the policies applied to the LPC chamber. And your code will be executed with elevated writes, which is good enough to give you access to the SMS or contacts and breaks out of the current chamber. So what do you do once you've done this? You're thinking about post-exploitation. Like, for example, extracting sensitive data from the phone. You might want to even eavesdrop on the user, install a rootkit. But if you're a malware writer, you might want to disable policies or the code signing protections as well, so you can get your malicious code onto the device at a later date without these protections. So turns out that HTC had something. I mean, what is a policy faker and certificate faker? Like, these are just strings from the binary. I haven't fully reverse engineered this, but this set like alarm bells ringing in my head. I was like, policy faker, really? Like, yeah. Also, license faker. I mean, DRM, anyone? Like, yeah. And I mentioned about the load verifier framework as well. So these are functions which are in a device driver which HTC has implemented. LV mods authenticate file, LV mods authorize. They look really suspiciously similar to the names of the actual legitimate functions. So this might be a way of deterring legitimate functions. And then you have strings like backdoor fixing developer unlock. Backdoor fixing, you know, that's like, come on guys. Like, yeah. So yeah, time for my demo. So this is a browser exploit. I'm loading Internet Explorer and browsing to a web page which says exploit me, but yeah. At the top, it's a web server. That's delivering the malicious payload, the browser exploit, to the phone over Wi-Fi. At the bottom, that's an exploit handler. The exploit handler is going to listen for a file transferred from the phone. So the phone's going to connect back to my exploit handler, transfer the database, transfer data from the phone. And there we see the that's actually the browser history, which I've transferred back from the phone over this reverse connect back socket. So my conclusions really are that it seems that Microsoft have put a lot of security thought into the phone when they've been making their architectural and design choices when they were designing the OS. But the OEMs potentially break the security model, and potentially, because Microsoft have allowed the OEMs additional functionality, then this increases the risk to the phones as well. The OEM choice can influence the security. It's not just the same across the board depending on what OEM you go for. It also means that attackers can use OEM vulnerabilities. So if you're targeting Samsung or targeting HTC, then you can deliver a targeted payload for the phone to do your privilege escalation if you can't find any bugs in base operating system code. But ultimately as well, it demonstrates that an attacker needs multiple vulnerabilities to attack the platform. It's not just straight one vulnerability. It's a case of two or three vulnerabilities and an exploit mitigation to actually attack the platform. I hope to provide more details in the white paper, in my white paper and advisory documents in future. So, are there any questions? Okay.
They're running over there.
Yeah.
So you actually exploited the vulnerability in ID,
Yeah.
not using the COM region.
No, that was the Internet Explorer vulnerability to gain additional code execution.
So there's another possibility to use, as you know, to use a COM region class to run native.
Yeah.
So it is not using for this.
You can use the COM, so Barak is saying that you can use the COM bridge to execute native code. You can, yeah, you can use the COM bridge the COM bridge is used to perform the privilege escalation to break out of the sandbox. However, yeah, so if an application has this ID cap interrupt services, then you can escalate your privileges up from the least privileged chamber to access more security critical functionality, really.
So it is used in this.
That's actually just the initial stage, the browser vulnerability, and the exploit mitigation bypasses to gain code execution. I ran out of time when trying to chain the kernel exploits as well together with the Internet Explorer exploit, but I think that should be potentially doable. So, yeah.
Any other questions? Yeah, where is that?
Yeah, where?
Any idea where it's coming from? Question about
experience that if we're looking to do early deployments, what's a good manufacturer to go for that has at least backdoors and fakers built into it?
I think you need to consider all the manufacturers and really do a review of the security of all the devices on the market, because I've not looked at a number of, I've only looked at 2 OEMs. I've not looked at the other 3 or 4, I think. So I couldn't really, I can't really advise you on that, so, unfortunately.
any other questions other than what's that dog noise?
How big a vulnerability is it? I mean, if you're wandering around with your phone, you know.
So this is essentially a drive-by browser exploit. You don't need to click that link. The link was just there to demonstrate the vulnerability. If you browse to a malicious web page, then that could all be automated to steal files off your phone.
What I mean is, are we likely to see the level of malware that we see with sort of general purpose computers deployed using this kind of technique? Or?
I would say not, because the architecture has been deployed with security in mind. It's been locked down. It's a closed operating system. you don't have access to the functionality which you have on the standard PC, so likely not in this case.
What's that vulnerability to JPEG?
Okay, so the vulnerability, so Bio's asking whether it's the JPEG vulnerability. The vulnerabilities, it's running into the Explorer 7. Mango's out soon, really soon. But I'm not going to disclose what vulnerability is. Because it's, they're potentially, Mango has gone to RTM at the moment. So, but I don't know how easily it is to get hold of for the general public at the moment. Developers, I think, can have access to it, but I won't say what vulnerability is. It's not there.
Any other questions other than where does the vulnerability lie and what's the dog done? Gentleman at the back there.
How do you consider email as a
HTML email. Well, so the guy at the back's asking whether HTML email is a potential vector. Every attack surface on mobile phones is a potential vector to gain code executions. So it's just a case of choosing what the most likely one is to, what the easiest one is to exploit. I chose the browser because I knew it was running IE7 as opposed to IE9 on. But yeah, HTML email, yeah, this could potentially be vulnerabilities in code which handles that. Yeah, don't see why not.
Any more questions? Anyone? Okay. All right, well, we'd like to say thanks to Alex for a wonderful talk.